Okay, so we are next ready to start Jordan form. This is another of the canonical forms. And this is how the section starts. Say we have a finite dimensional vector space. Let V be a finite dimensional vector space over some field F, and let T be a linear operator on V. Okay, let V1 be a subspace of V that is invariant under T. We know what that means. It means that the image of V under T is again a subset of V. And let Qx be a polynomial over F. Okay, now because V1 is invariant under T, so we already know, we have seen these things before, that T will induce an operator on V1 itself, which will be a linear operator on V1. Let that be T1. Let T induce the operator T1 on V1. Now this is the claim. If we evaluate this polynomial at T, in other words, if we substitute x for T, then we will get the operator Q of T. That is also an operator on V. So we can restrict that operator as well on the subspace V1, just like restricting T on V1 gives us T1. So what shall we get if we restrict Q of T on V1? The claim is that we are going to get Q of T1. Let's see if that's true. For that, what do we have to do? We are going to take an arbitrary vector from V1, and on that vector we are going to apply Q of T. But because we need to see what's going to happen exactly, so let's write what the polynomial Q of x is. Let's write its general form. Let Q of x be, say, a n x to the power n, like that, where it's of course understood that these ai's are coming from the underlying field F. Now, for any V coming from the subspace V1, let's see what we get if we calculate VQ of T. That is the image of the vector V under the operator Q of T. So if we now write what Q of T actually is, it will look like this, plus I have to continue on that side. It's not a very complicated calculation. It's just going to be ultimately equal to V of Q of T1. We just need to see that it really happens, that's all. Plus A1T plus A0. Now if you want, you can keep this A0 as A0, but if you really want to not misinterpret it and forget that this is not merely a scalar, you can write either 1 here or I here, capital I, which is the identity operator. So let's just write this, because the identity operator is the unit element in the operator algebra A of V, so we can also write 1. Now what will it become? By the definition of addition, scalar multiplication, all these operations in our operator algebra, this thing is equal to this. If you want to really emphasize the fact that we are multiplying a vector by a scalar, you can use parentheses like that here also. So this, for example, is a scalar multiple of the vector, which is the image of V under the operator t to the power n by the scalar an. Like that, the other terms also are interpreted. Plus a1 V of t plus a0 V. Well, if you want, you can write one more step. Say first you apply the operator, identity operator on V, and then it's going to be just V, because that's what identity is. Okay. Now let's see. The thing here is that I want to write this. In place of t, I am writing t1. Is it justified? Yes, it is justified. Why? Because you see, our subspace V1, from where this V is coming, is invariant under T. This means that the image of V1 under T is contained in V1. So, no matter how many times you apply our operator T on a vector which is coming from V1, the result is going to lie in V1 every time. And that is why, because of this fact, this is also true. Because what is this? This is the T image of V1T. Because V1T is already a subset of V1, and V1 itself is invariant under T. I mean, do you get the point? Say you apply T square on V, where the V is that V. Then what is this? It's the T image of Vt. Vt is, after all, again a vector in V1. And V1 is invariant under T. So its own T image is again going to be a vector in V1. Okay. And that is why we can just simply write the restriction here. I mean the operator that T induces on V1, which is our T1. Similarly, an minus 1 V T1 to the power n minus 1. Plus a1 Vt1, and this of course you can just keep it like that. And that's why if you now do kind of back calculation with t1 in place of t, you get this. Actually, if you really want to be absolutely rigorous, this one and this one are not exactly the same identity operator. This one is the identity function on the space V. It's a function from V into V, onto V actually. This one, however, is the identity function from V1 to V1. But because we are just using 1 to denote the identity element of any operator algebra, so we do not bother to distinguish them by using different symbols. I mean, it won't serve any purpose, because anyway now this is going to collapse into this. It will now be equal to V Q of T1. And we started with V Q of T, so we can now write our conclusion. So, Q of T induces the operator Q of T1 on V1. Okay, so that was our claim. Now, a particular consequence of this fact is this. In particular, if Q is an annihilating polynomial for T, that is, when you evaluate Q of T, you get the zero operator. Then Q of T1 is also equal to 0. Why? Because Q of T1, you see, we are saying that Q of T induces the operator Q of T1 on V1. In simple language, this just means that if you restrict this function, which has domain V, to the subset V1, the restriction is this. So, if the entire function is identically 0, then the restriction is also 0. That is, T1 satisfies any polynomial that T satisfies. And then the author asks, what can we say in the other direction? Say it in the other direction. And to answer this question, we have this next lemma, where actually things start really. So the setup is same. V is a finite dimensional vector space and T is a linear operator on V. So the author is not again going to repeat these things, okay. The statement is not like that. It's understood that these things are already there. Instead, it starts like this: let V be the direct sum of two subspaces, V1 and V2, where V1 and V2 are subspaces of V invariant under T. Okay. Let T induce, because each one of them is invariant under T, so T will induce an operator on each one of them. Let us call these operators T1 and T2. Let T induce T1 on V1 and T2 on V2. Okay. Now, if P1 of x is the minimal polynomial of T1 over F, and similarly we have the minimal polynomial for T2 also, for T1 over F and T2 of x be that, means it's also the minimal polynomial, but for T2 over F, then the minimal polynomial for T over F, that means our original operator, is the least common multiple of P1 of x and P2 of x. Now, before we see the proof, let me just put some ink. I forgot. Okay, so just give me a moment. And also, before we start the proof, you may notice something about this statement. See, whenever we say LCM of two polynomials, what comes in your mind? I mean, do you recall something from ring theory? In ring theory, if you remember, we proved that the polynomial ring over any field, polynomial ring in one variable over any field, is a Euclidean domain. And that thing for us is fx, fx within square brackets. And in a Euclidean domain, we know that any two non-zero elements have an LCM. For GCD of two elements to exist, one of them may be 0, but for LCM, both of them need to be non-zero. Is that really the case here? I mean, at least we can see that in the beginning itself, because otherwise we cannot talk about LCM. The LCM does not exist if even one of these two polynomials is 0. But they are not 0. Why? Because by definition they are minimal polynomials, and hence they are non-zero polynomials, where if you put the respective operators, then you are going to get the zero operator on that subspace. And these are polynomials with that property, but at the same time having the smallest degree. So by definition, these are non-zero elements in the Euclidean ring Fx. So their LCM exists. Okay, from the theory of Euclidean rings, we know that their LCM exists. So we do not have to worry about the existence of LCM. It exists, we know. Okay, so now let's see the proof. Alright, so the proof goes like this. First, the author has taken the minimal polynomial, and consider the minimal polynomial of our original operator t. Let p of x be the minimal polynomial of t for t same thing over f. And for convenience, let's also consider something else, and let q of x be the least common multiple of p1 of x and p2 of x. And as I remarked just now, this exists, okay, because it's coming from that theory. Alright, so now what can we say about this p immediately? Because it's the minimal polynomial for t over f, if you calculate p of t, it will be the zero operator. Now, p of t is equal to 0. Now, because what are t1 and t2? t1 is the restriction of t on v1 and t2 is the restriction of t on v2. Because p of t is the zero operator, and whatever we discussed in the beginning, what will be the restriction of p of t on v1? That will be p of t1, that's what we saw there, right? So if we restrict p of t on the subspace v1, then that restriction is nothing but p of t1. Similarly, restricting p of t on v2 gives us p of v2. And because the original operator is identically 0, that's what zero operator is, right? You apply it on any vector, you get the zero vector as result, as output. So if the original operator is identically 0, then obviously the restrictions are also going to be 0. Zero operators on the respective subspaces. So p of t1 is equal to 0 and p of t2 is also equal to 0. But now what does it say? How can we link this with the minimal polynomials for t1 and t2, which are p1 and p2? Well, this p, not these are, this single p is an annihilating polynomial for both t1 and t2 because of these things. But p1 is the minimal polynomial for t1, and this is any annihilating polynomial. So from properties of annihilating and minimal polynomials, we know that p1 will divide p of x. this implies, and again that fact comes from properties of Euclidean rings. Any annihilating polynomial is always divisible by the minimal polynomial. And this also happens due to the Euclidean algorithm, which otherwise is also known as the division algorithm, and the fact that a minimal polynomial is an annihilating polynomial of smallest degree. That's why this divisibility happens. So this implies the minimal polynomial of T1 is going to divide this annihilating polynomial of T1. And also, because of this second equation, the minimal polynomial for T2 divides this annihilating polynomial. Okay, now you recall the definition of LCM. What is an LCM? An LCM is, in a Euclidean ring, is a ring element. Obviously you have to have two elements first. Say E is a Euclidean ring and A and B are two elements in it, both of which are non-zero. An element C in E is said to be an LCM. I say an LCM because usually it's not unique in Euclidean rings. An LCM of A and B is an element C such that A divides C and B divides C. This is one condition. And the other condition is this, that if D is an element in E such that A divides D and B divides D as well, then C also has to divide D. Okay, so if these things happen, then we call C an LCM of A and B. Now, this is our LCM of P1 of x and P2 of x. And this P of x is playing the role of this D, some other multiple of A and B. D is any common multiple of A and B, and C is the least common multiple. So, C has to divide D. In this case, Q of x has to divide Px. Hence, Q of x divides Px. Okay, so we get one divisibility relation. Now we want the other divisibility relation. And for that, let's see what we can do next. So next we are going to consider any element in V, and we are going to use the fact that V is the direct sum of V1 and V2. So let V be any element in V. Then, because V is the direct sum of the subspaces V1 and V2, so our vector V is a sum like this, where V1 is coming from V1 and V2 is coming from V2. Actually, due to the fact that the sum is direct, this expression is going to be unique. I mean, for that we are going to get only one V1 from V1 and one V2 from V2, for which this thing happens. But that uniqueness is not used here. All right. Now, what do we get if we calculate the q of t image of the vector v1? We are coming to v afterwards, but let us see what this is. So this is going to be v1 q of t1. Why? Why am I able to write t1 here? Well, we are again using our first observation that when we take a vector v1 from a subspace v1 which is invariant under T, then q of t, if you restrict q of t on the subspace v1, then that restriction is precisely q of t1, where t1 is the restriction of t on v1. That's why. Alright. Now, what is q? Q is the least common multiple of p1x and p2x. This means what? This means that in particular, for example, p1 of x divides qx. Okay, it also means other things, but p1 of x divides qx. And that's why qx will be equal to p1 of x times something, some polynomial, say r of x. Alright. Now, if you replace x with t, what will you get? Q of t is equal to p1 of t times r of t. We are not bothered about r of t, but what is p1 of t? Oh, well, actually t1. Yeah, why am I again writing t? t1. What is p1 of t1? You see, p1 is the minimal polynomial for t1. So it's also an annihilating polynomial for t1. It will annihilate t1 means it will, if you evaluate p1 at t1, you are going to get the zero operator on v1. R of t1. So you are getting the zero operator, and that is why this will be equal to v1 0, which is equal to the zero vector, and similarly if we calculate this, then because this time v2 is coming from v2, so this is q of t2. But just like q is the LCM of p1 and it's divisible by p1, it's also divisible by p2, and that is why q will be a multiple of p2 as well. So if you evaluate q at t2 like that, you are going to get the zero operator, but this time on the subspace v2. So this is also getting you 0. So what is the consequence of all these things now? So having calculated these two things, we can now calculate the image of V under Q of T. This is equal to V1 plus V2 Q of T. Q of T is after all a linear operator, so it will respect addition. But what was V? V was any vector in V. That means our operator Q of t is identically 0. It's the 0 operator. Since V belonging to V is arbitrary, we have Q of t equal to 0. Okay. So now Q becomes not a minimal polynomial. What I wanted to say is that Q is an annihilating polynomial for the original operator t. And what is the minimal polynomial for our original operator t? P. So minimal divides annihilating. That's why P of x divides Q of x. Now we have these two divisibility relations. What can you conclude from them? Are you going to immediately conclude that P of x is equal to Q of x? Well, it will be, but in general, these two divisibility relations in a Euclidean ring doesn't imply equality in general. It implies that each one is an associate of the other. That is, each one is a unit times the other. Okay, that's what it implies. If you go back to the section on Euclidean rings, there you will see a lemma which says precisely this. However, in this case, we are going to get equality, but why? Because of the fact that we have defined minimal polynomials to be monic polynomials. You see, what is P of x? P of x is the minimal polynomial for t. So by definition, it's monic, and this monicness actually makes it unique. Without this extra condition, if we simply assume that a minimal polynomial is an annihilating polynomial of smallest degree, then there will be many such polynomials. But monicness ensures that we get only one such polynomial. And you know what monicness is. It means that the leading coefficient of the polynomial is 1. So this is one such polynomial. And what about Q of x? Q of x is the LCM of, again, two minimal polynomials, P1 of x and P2 of x. So Q of x is also going to be monic. And that is why from these two things and combining the monicness of these two polynomials, we get equality. I am not going to elaborate more on this. I will just simply write this. Hence, P of x is equal to Q of x. You know why. And this is the minimal polynomial for our original operator t, and this is the LCM of the minimal polynomials of t1 and t2. That's what we wanted to prove, right? So the proof ends here. And this result, this lemma, has a natural corollary where instead of necessarily two subspaces, we have any number of subspaces. And the proof of the corollary, of course, can be done by induction. So it's straightforward. So we are not going to go through the proof. We simply see the statement. Let phi be the direct sum of a number of subspaces where each Vi is a subspace of V invariant under T. Okay, what else do we need? We are going to need those restrictions. Let T induce Ti on Vi for each I if Pi of x is the minimal polynomial for Ti over F. That's understood. Okay, if you want you can write it here. Then the minimal polynomial for T over F is their LCM. Is the least common multiple of these polynomials. Oh, and just like we have the LCM of two non-zero elements in a Euclidean ring, we also have the LCM of finitely many non-zero elements. All of them need to be non-zero. And the definition of LCM of any finite number of elements in a Euclidean ring is exactly similar to the one having two elements. Okay, there is no change other than the number of elements. So we have this corollary. So let me just end the video here itself. So after this we will see in the next linear algebra video where we can go with this. You can see why we are calling this section a decomposition of V. Okay, and just like that previous nilpotent form or nilpotent transformation, it has a definite form. So this time also, Jordan form is going to give us a particular type of matrix, again based on some decomposition of V. So that's just it, and tomorrow we have our usual real analysis, where what exactly are we doing right now? I don't remember if we completed I think we completed the section on integrability of continuous functions. So tomorrow, if that's the case, then tomorrow there will be a community post, not a video. In that community post, we will solve exercises. So let's see what we have tomorrow. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.